Hi everyone, how's it going? We're going to move on from the previous section, which was 5.2, and to 5.3, so volumes by cylindrical shells. So we were calculating volumes last time using two main things. We had the disk, which remember we were just using a solid filled in disk. So these are our cross sections. So there's doing disk in a circle is the circle is like the outside of the disk, but the disk is like the whole thing. It's like a frisbee basically. And then we also had washers. So those were like these. So we were using this part to calculate the cross-sectional area. So if there wasn't a hole that we needed to like account for, then we use the disk. If there was a hole and we needed to like exclude certain parts of our shape to not count that volume, we use the washer. But now here's another method called cylindrical shells. And so what is a cylindrical shell? Well, let's think about this cup here. If we take the handle away, ignore the handle, notice that the inside is basically empty, and it has like a very thin, it's not so thick, but it has this very small thickness to it. So this outer region, the shell of the cylinder, so if you take the handle away, it's a cylinder. The shell of the cylinder, this little outside part, accounts for some little volume. And we're going to use that as basically the thing to count volume. We're going to add up this volume of very thin shells like this, and just like how the integral works, that'll end up giving us the perfect answer once we add up all these smaller volumes. So the general picture for the cylindrical shell is this guy here. So we have a cylinder, and then the shell of it. So we're just looking at this outside part. So we're looking at the cylindrical shell. Now, so like in terms of the cup, this was like that really small thick part here. Really small part here. This is like drawn larger as exaggeration. But the outside part of the cylinder, that has a little bit of volume, and that's what we mean by the cylindrical shell. Now, we want to approximate the volume of this guy. Now, the book goes through the technical details of it, but we'll just skip it. But the idea is that you want to multiply three things, three different distances. And why? Because remember, when you take a length, the unit of that, let's say, for example, is a meter. So length is a one-dimensional thing, so it's a meter. When you get area, it's a meter squared, right? So you take the product of two different lengths. Like think about the area of a square. It's the product of the base times the height. So that's a product of two lengths. So you get like meters squared. And then a volume is the product of three different lengths. So you get like meters cubed as the units. So here we want to multiply three different lengths. So the volume of this guy is going to be the circumference times the thickness times the height. This will be the volume of our cylindrical shell. Okay. Now, if we think about this in the context of a problem, we'll see pretty quickly how we can figure out what these are basically. What is the circumference, what is the thickness, and what is the height? So let's look at this like in kind of a general setting. So say we have this shape here. we have this little arc here, and then this is A to B. And we're going to take this arc and we're going to rotate it about the y-axis. So and again, this is coming like out of the board and into the board, so it really makes a three-dimensional object. It's kind of hard to draw perfectly, but when it rotates like this, you get that. So when it rotates about the y-axis, at least when it ends on the other side, you get this mirror image. But as it's rotating like this, it creates like a circle where each part of the circle has this little arc coming in and out of it. So it makes like this like kind of like bowl looking shape. Which again, my drawing skills are not like perfect, but this is the rough idea. So it makes like bowl looking shape. And so the cylinders that we construct, they are going to look like this. So say that we take this point X, and so we have a cylinder like this. Or let me erase this for a second. So we just let me draw one of these arbitrary cylinders. Okay. So this is one of the cylindrical shells that we're using. Now, what from here to here is the radius of the shell, right? You can go from here to there, but it's symmetric, right? So we'll call this point, this arbitrary point, X. So now that we know the radius of the shell, you can calculate its circumference. Remember, the circumference is 2 pi times the radius of the circle. So the circumference down here of this circle, this is 2 pi x. And then the thickness, so the thickness, I haven't drawn it in a way that you can see a thickness, but you know, it's going to be like this thing here. So it has some thickness here from here to here, which again we're just going to call dx because it's going in the x direction. Remember, the idea here is if you take really small, like if you let the number of cylinders or the number of rectangles when we did the area under the curve, if you let that go to infinity, then like the distance, the delta x gets replaced with dx. So this really small thickness we're going to call dx. Like this thing here. From here to here, this really small thickness, that's like dx. Okay, so then the thickness is dx. And then what is the height of the cylinder? Well, if this curve is given by some function, which it is, the curve is like some function f of x, whatever it is. Notice that if this is the point x, then this is f of x here. How high you go is f of x. And so this this drawing is not perfect because this shell should be from like the x-axis up, meaning that there shouldn't be like a gap here. It should be nice, and I don't know if I should fix it at this point. I might as well, it wouldn't hurt. So we at least have these two things. So we have the circumference and the thickness. Now we're just trying to get the height. So let me redraw this. This is A, this is B. When you reflect it, it looks like that, kind of. And then we get like this bowl looking thing. Kind of like this bowl. So you get this bowl looking object, and then when we make the cylinder, and so yeah, when we make the cylinder like this, this goes all the way down to the x-axis. Okay, I like this drawing more. Okay, so that's the cylindrical shell. Okay, and then this was the point X here that we had. So notice that the height of the cylinder is basically how high up you go on the function. It's f of x. Right? If I stick x into the function, how high do you go up to hit the point on the curve is f of x units. So the height is f of x. And so now we have the volume. So all we need to do is just add up the infinite amount of these shells to get the perfect volume. So then the volume, so this should probably say shell volume, just to be clear. This is the volume of the shell. So then the volume of our solid is going to be, again, we go from A to B here, as usual, and it's just going to be the product of these three things. So 2 pi x, f of x, dx. So this is the formula that we're going to use here. Okay, and the example we'll do next to actually find the volume will also show kind of why we need the cylindrical shells sometimes to make life easier, because in some scenarios it's very difficult to find with the disc in the washer method the volume of the solid. So let's just do an example here now. Okay, so if we think about the curve y equals 2x squared minus x cubed and y equals 0. So we're going to look at that. So what does this represent? So it looks like this guy. This is roughly what we have. Because this curve will go down here, but we stop it because y equals 0 is the x-axis basically. So we're taking this little hill looking thing and we're going to rotate this about the y-axis. So again, this little like bump is going to come out of the page and then hit the blackboard and then go in until it comes around and hits that again. So we can, roughly just maybe do the mirror image here, and then the rest you kind of have to think about how it comes out. I'll show you guys the picture from the book. It's a computer generated picture because it's a little difficult to draw with your hand, but it kind of just looks like a little like sinkhole. So it's like a bowl with like a sink, a dent in it. So the thing is here, why can't we use like the disc method and stuff like that? So remember, normally when we made the discs, if you wanted to, and then let me just get rid of this, because the mirror image here we don't really need, we don't have the whole shape. If you wanted to use the disc method to like calculate this thing here, you would need to know basically this radius here. Okay? But that's a little difficult because we don't, this function is a y equals function, right? So at any point x, it'll tell you how high you're going. Like if I pick this point x, it tells you more about how high you're going as opposed to the right. So that's already one issue because we need this. So you would probably need to solve this in the other way. So you would need to know whether the equation of this curve as like an x left, this thing here being x left, and this guy here being x right. you would kind of need to know the equations of these two curves. But to solve for that from this is, in general, a very difficult task. So it's maybe not worth it and stuff like that. And the same idea will happen with the washer. Like if you try and use a washer or whatever, the same thing will happen. It's just even worse. So here the cylindrical shell is the best option, because the shell stacks up very nicely. Because we stack it like this, it'll be able to account for this part very easily. So that's why this method sometimes is a little better in some scenarios. So okay, back to, so this guy's here. So then, like usual, we want to set up the shell here. So make one of the shells, just an arbitrary shell. And then again, this hits the x-axis. And then okay, so that's what the shell looks like. So as usual, we don't have to rederive all of this. All we really need, because we know that the volume of our solid is going to be the integral from something to something of 2 pi x, because remember we determined that the radius from here to here, that's just at some point x. The radius is x, so the circumference is 2 pi x. And then you multiply this by f of x dx. And we have a formula for f of x. It's this guy here. So we don't have to do much work really. Now notice that this is one thing kind of different from the disc and washer method, is when we rotate it about the y-axis normally, we would use a dy. But here with the shell method, the cylindrical shells, when we rotate about the y-axis, we use dx. And it's just because of the way that we're stacking the shells. The shells are going up and down, but the radius then is being measured from like right to left. And we'll see an example of opposite here in a second. But we kind of have the formula already, so we just need to figure out the limits of integration. And to do that, you just need to know what this point here is and this point here is. And that's exactly when this function has an output of 0. So you just set this thing equal to 0, and you get this. So if you pull out an x squared, you have this, so you get x squared is 0, or 2 minus x is 0. And then that just tells you either x is 0 or x is 2. So exactly, we know that this is 0, and then this is 2, and those will be the limits of integration, because we're going from a to b here, 0 to 2. So now that we have this set up, let's just do the integral, or at least expand it out. I think at this point, you guys are comfortable with finding the integral and stuff like that. So the volume will be the integral from 0 to 2 of 2 pi x times f of x. Well, what was f of x? It was 2x cubed, 2x squared minus x cubed, 2x squared minus x cubed times. So 2 pi x, f of x, that's f of x, 2 pi x, and then dx is what we have. Okay. And then this is equal to just, right, the 2 pi x can distribute to each piece. But if you think about it, the 2 pi is just a constant that you can pull out in front. So really you can just pull the 2 pi out in front of everything. And then we have just x times all of this. Alright, we can't pull the x out because the x is not a constant. You can only pull the constant out of the integral. Variables you cannot pull out. So this is 2 pi now. And then just distribute the x. So you get 2x cubed minus x to the 4th dx. And then now you can take the antiderivative, or the integral. So if you use the power rule here, this is going to be 2x to the 4th over 4, right? Just add 1, minus then 1/5 x to the 5th here for this guy. And we evaluate that from 0 to 2. And this is just 2 pi times now 1/2 x to the 4th minus 1/5 x to the 5th, evaluated from 0 to 2. Which will just be 2 pi times, stick 2 into this, so you get 1/2 2 to the 4th minus 1/5 2 to the 5th minus 2 pi times just 0 and 0, right? 1/2 0 to the 4th minus 1/5 0 to the 5th. So this will be 0. And then when you do everything here, you get the final answer of 16/5 pi. Okay. So yeah, you can see that the cylindrical shell method sometimes it makes things that would be much more difficult more convenient. So it's good to just have both of these in your arsenal. Okay, now let's do another example. Another example is this. Oh, sorry, let me write it out. So we've done this one before. So it's the curve y equals x and y equals x squared. So the region that those create, so with their intersecting points, that little strip, remember, that we got from that about the y-axis. Okay, and this was an example where we needed the washers. We needed a washer to take care of this. I think maybe we rotated this about the x-axis. I'm not sure, but either way, you'll need a washer to do this. But the shell method can also handle this. So remember that these intersect at the ordered pair 0, 0. And 1, 1, and that the line is on top of the parabola. So those are things that we remember. And then if we rotate this about the y-axis, then we get this shape here. And again, remember that that created like some like bowl looking type thing, and you know. So now the thing is that when we make these shells, they'll look like this. So the shells will look like this, because they'll start at this top curve and they'll end at the bottom curve. So that's one new thing. So again, we always have the 2 pi x dx. We always have that. That is given because, again, in this scenario, what would the radius be? Going from here to here, we'll just call this random point x. So the radius is x, so the circumference is 2 pi x, because it's 2 pi times the radius. And then the thickness is always dx. So the only thing that we have to really figure out is like the height, because this is going to be height times this. And normally this is just f of x, but here we have two functions, right? We have this function and that function. So what is the height? Well, the height is this point to that point. This is let's see. How can I draw this to be more accurate? So let's see. There we go. This is better drawings to represent what's going on. Okay. So this is the height we're looking for is from this point to that point. This is the height. So from that point to this one is the height that we're looking for. And so what is that height? Well, it's the y top minus the y bottom, right? Because up here is what happens when you stick x into the line is you just get x out, right? And then when you stick x into this function, you get x squared out. So it's the height you get here minus the height here, that gives you this little sliver. So the height is going to be basically y top minus y bottom. That's what the height is. And in this case, that's going to be equal to x minus x squared. So when the function didn't have a y top and a y bottom, and the bottom was just like the x-axis in the last example, you know, it was just a function minus 0 then. That's why we didn't see anything. The y bottom was just 0 because it's the x-axis. Because y equals 0 is the x-axis. So we got y top minus 0, which is just y top. And that was just the function that we were already considering. So in this case, now the volume will be the integral from 0 to 1. Remember the ordered pairs were this. So we go from this x coordinate to that x coordinate. And then as always, it's 2 pi x. Now this thing here, the height was, like we said, y top minus y bottom. And then times the thickness dx. So remember, this was circumference. This here is the height, and this is the thickness. Okay. So then this is pretty similar to the last problem. Is again, you could just pull the 2 pi out, and then you're just left with the x here. And then the x distributes. So you get x times x, which is x squared. And then x times negative x squared is x cubed. Okay. And then at this point, you just take the integral. So this is 2 pi times 1/3 x cubed minus 1/4 x to the 4th. And then evaluate that from 0 to 1. Which, when everything clears, that's pi over 6. So in some cases, yeah, you can use either method. It doesn't matter. And it's kind of just up to you. It's a choice. Okay. And then for our last example, let's do one where we rotate it now about the x-axis. Now if you think about it, when we rotate about the x-axis, the shells will line up like this. They'll look like this. They're going to look like that. And so, you know, instead of having a radius of x, because normally when they're like this, from here to here was the radius. That you measured in the x direction. Here, you're going to go up and down, so you're going in the y direction. So you can already see what's going to happen is the volume will be the integral from, again, some a to b, we don't know. But now it'll be 2 pi y, and then it'll be some function of y, and dy will be the thickness. Because now the thickness is not in the x direction, it's in the y direction. So the key will be just to find this f of y here. Okay, and let's just do that. So we're going to use, we're going to take root x, let's say y equals root x. So that function from 0 to 1 around x-axis. So this is our example. So remember that we've done this one before. It's going to be the square root of x, like this. If you stick 0 into this guy, you get that. If you stick 1 into it, you get 1. So this is a 1 unit up. When you're 1 to the right, you're 1 up. And then x equals 0, remember, as just this line, aka the y-axis. And x equals 1 is the vertical line 1 unit up. So the part that we care about is this. So the region that we're looking at is the one created by these guys here. And then we rotate that about the x-axis so that we get this thing here. And it looks like this little bowl looking thing. Maybe let me draw it a little better. There we go. It'll look on the inside. So this is at 1 unit to the right. Okay, so we have this bowl. Now we have to think about the way that the cylinders will look. So this thing is going like this, right? From left to right, so our cylinders should stack up that way too. So our cylinders will stack up in the opposite way like I was talking about. So here now, the cylinders will go from here into like this point here. So the cylinders will look like this. So the cylinder will look something like that. And you might be thinking, why are we going to this point? Why does the cylinder not start here? Notice we go this way. If the cylinder started here and ended there, we're taking into account regions that are not in our shape. So you always want to go to the point in the shape. You want to keep the cylinder within the object whose volume you're trying to find. Okay, so this is what we have. Now we need the circumference. So we need the circumference, which again is just 2 pi times the radius. So what is the radius here? Well, the radius goes from here to here, right? From here to here, which I can just call that some arbitrary point y. So the radius is going to be 2 pi times y. Or sorry, the circumference will be 2 pi y. And then remember the thickness was dx, but in this case it's going to be dy. Because now we're going, the shells are opening up this way as opposed to like this. This way is a dx, this way is a dy. And then now the height is the key thing here. Is if we think about this function here, y equals root x. If you square both sides, you would get that y squared equals x. So you can think of this as a function of y now. I give you a y coordinate, and that tells you what x should be. So we want to think about it in this sense, and we'll see why in a second, why this is nice. Because notice that if we pick this point y, this is an arbitrary point y, if you square it, this tells you how far to the right to go. So this point x here, that equals y squared. Whatever that point y you picked in determining the radius, if you square that number, that tells you how far from the origin you are to that point. So that, you may be like, how does that give you the height? Well, we're close, right? That tells you this distance, but we need actually the one here. But we know from here all the way to here is 1, right? So this big distance is 1. So if we subtract this distance that we found from it, we will know the intermediate distance. So the height is actually 1 minus y squared. And now we have everything we need. Now we know that the volume is the integral from, some a to b. You probably can hear that, it's 12 o'clock. What is our a and our b? So we're going on the y-axis now. Because we have a dy, we need to go from some point on the y-axis to another one. Well, we start at 0 and we end at 1. And then we multiply circumference, the height, and then the thickness. So this will be the formula for the volume. And then at this point, I believe that you guys are well equipped enough to know how to deal with this. So I'll leave this to you guys, and then if you have questions, feel free to ask me in class. And then let me check on the time. Okay, so now we can jump to section 5.5, which is the average value of a function. So we're done with all the volume stuff, and we skip 5.4. So at first this may seem weird, the average value of a function. So let's just think about what the average of like a collection of numbers is, right? Say you have 4 test scores, 81, 90, 70, and 64. What is the average of these 4 test scores? Well, what do? You just replace, you just add these up, and you divide by 4. That's the average. So in general, if you have n things, y1, y2, all the way up to yn, what is the average of these things? Well, it's y1 plus y2 plus y3 up to yn minus 1, and then yn all over n. So you add up all the n things and you divide by n. Okay, so that's the average, right? So if we think about a function and average value, meaning the output of the function, if we have a function, let's say we pick some sample points. So then this point here, so we have our function, and then we take just a few sample points on the domain that we're considering. You could take more, you could take less. Then you take x1, then the output here is f of x1. And then if you take x2, the output here is f of x2. And then same thing here. This output right there is f of x3. And then this one is pretty dang close to it, almost identical, slightly above it, is f of x4. But you get the point, right? These are the values of the function, the outputs. So the inputs, they're just inputs. The value the function takes are the corresponding outputs. And you know, so we can kind of say, okay, if we think that these 4 points are representative of the average value, which may or may not be true, then the average value, an approximate average, would be just you add up these guys, the outputs, and you divide by 4. Okay. So then in general, this would be, you know, if we didn't use 4 points, but we used n points, the approximate average would be this. So now you just add up the n points, you add up the outputs of the n sample points that you used, and you would divide this by n. Okay? Now this is probably making you think of some stuff like, hey, we talked about, this idea sounds really familiar. And yes, it's like the kind of the stuff that we did with the Riemann sums, you know, where we picked sample points and then we looked at the outputs. And so, going back to that whole Riemann sum business, remember that delta x was equal to b minus a all over n, right? So remember the function I drew roughly looked like this. This was a, and this is b. So we want the average value from a to b. So, you know, because the function could go on forever, but we just mean between a and b, what is its average value? So this gives context to what a and b are. And so if we do a little bit of algebra, you can rewrite this as n times delta x is b minus a. And then if you divide everything by delta x, you would get that n is b minus a over delta x, which we're going to stick in for that n now. So when you do that, what do you get? You get f of x1 up to, so the sum of those guys, all over b minus a over delta x. Which again, anytime you're dividing something by a fraction, you just end up multiplying by its reciprocal. So this ends up being delta x times this guy running out of space, maybe one less thing. So you take delta x, multiply it by this entire sum, this big sum here, and then you divide this by b minus a. Which now, instead of dividing by b minus a, we'll just write it as 1 over b minus a times delta x times this thing. Okay, and at this point, is a good point to stop and think what would happen if we let how would you get the perfect average value? Instead of using a finite number of points, you would use like an infinite amount of points, right? So you would basically want to take the limit as n goes to infinity of this, because this is approximate average value. This is the approximate average. The actual average would be equal to if we take the limit as n goes to infinity of this. And now what's a quicker way of writing all this? A faster way of writing this is using the sigma notation, right? Because this just means add up f of x1 plus f of x2 plus f of x3 all the way up to n. That's what this means. So the actual average, the perfect average, is what happens when we let this go to infinity. The number of sample points go to infinity. But what we talked about is when you do this, remember that this delta x turns into a dx, and you replace this sigma symbol with the squiggly integral symbol. So the average value of a function, the formula is, the true average value is going to be this, is 1 over b minus a, the integral from now a to b, because that's what we're looking at, the domain, of f of x dx. So this is how we reason having the formula for the average value. Okay, very important. And let's just do like a quick example that we already know the example to. Say your function is a constant. It never changes on the interval a to b. So suppose that you look at the function that has a value of 2. Let's say this goes to 4, between 0 and 4. It never changes. What is the average value of this function? Well, it only has one value. It's always 2. So the average value should also be 2, right? So let's see what happens when we plug it into this formula. The formula would tell us that the average value is 1 over 4 minus 0. The integral goes from 0 to 4 of our function, which the function is just 2, right? F of x equals 2, aka y equals 2, of just 2 dx. Okay? And so this is now 1/4. And then remember, if you have a constant, its integral is just tack on an x. So this is 1/4 times 2x evaluated from 0 to 4. And then what does this give us? So this 1/4 and this 2 cancel out, essentially, to give us just 1/2 x evaluated from 0 to 4. And then this just becomes 1/2 times 4 minus 1/2 times 0, which is 2. Hey, look, that is the average value of our function. So this function never changes, so its average value should be that constant value. So this is a good sanity check. Now let's do something maybe a little more, I guess, more interesting you can think of. Maybe that way the function actually moves. So let's do f of x is 1 plus x squared on -1 to 2. Okay? Say we want the average value here. So f AVE, this is kind of like the notation for it, f average is going to be 1 over b minus a, so 2 minus -1, times the integral from -1 to 2 of 1 plus x squared dx. Okay, so this is 1/3. And then what's this antiderivative? It's x plus 1/3 x cubed, right? Because this is a constant, you tack on an x to it, so you get 1 times x, which is x, plus then the power rule is 1/3 x cubed. And then you evaluate this from -1 to 2, which ends up giving you just 2. So the average value of this function is 2 as well. And just to graph this guy, this is a parabola that opens upward. It opens upward. At 0, it's 1 unit high. So it starts down here and it opens up. And so at 2, when you stick 2 in here, you get 2 squared, which is 4 plus 1 is 5. So it's at 5 up here. And then at -1, when you stick -1 in here, you get 1 plus -1 squared. So that's 1 plus +1, which is 2. So it's up at 2 here. So the function that we're looking at looks like this. So this is roughly what we're looking at, is this arc. And between 1 and 5, those are the values that the function takes on. The average of all of those is 2. That's kind of what it's saying. Which is interesting. This concept may seem kind of random. It has a lot more powerful theoretical applications. And that being, this theoretical application I'm talking about is the mean value theorem for integrals. So mean value theorem, where have we heard that before? So remember, for derivatives, what the mean value theorem said is that if you have a function on a to b, then this line here, remember we called this the secant line, this line has a certain slope. Secant line has slope. Well, what is a slope? Well, at A, your f of A units up, and at B, your f of B units up. And what is the slope of a line? It's final output minus initial output all over final input minus initial input, aka change in the y coordinates divided by the change in the x coordinates. So this line has the following slope. Then the mean value theorem said that there is at least some other point, C, at least one, given certain conditions like differentiability, continuity, such that the slope of the tangent line always hard to find the exact point and draw it perfectly, that the slope of the tangent line, so for example this point C, the slope of this line, the tangent line, remember we denoted the slope of the tangent line at any point as f prime of that point. So f prime of C is the slope of this tangent line. So notice that these two lines are parallel. When two lines are parallel, it means they have the same slope. So what the mean value theorem for derivatives said is that there's at least one point between A and B where the slope of the tangent line is the same as the slope of the secant line, aka f prime of C equals all of this. And this has amazing uses, like it's used in the proof of the fundamental theorem of calculus. And so it's a very powerful result, even though it doesn't seem like it. So there's an analog to this with integrals. It's pretty similar. It tells you that there's some point C or whatever. But let's write it down. So let's see. It says some mean value theorem. For integrals. So suppose f is continuous. On the interval that we're considering. So all you need is continuity. Then there is a number C between A and B such that, okay, so again there's some number between the two endpoints such that when you stick that number into the function, that is the same as the average value. So that this input has the output of the average value, which makes a lot of sense, right? If the function does have an average value, there had to be an input that it was achieved at. So there's some input where when you stick it into the function, that output is the corresponding average value. But in terms of more symbols, this is that. Or equivalently, if you multiply both sides by b minus a, this means that f of c times b minus a, this whole quantity, equals that. Which this one is kind of more interesting. So it's saying that the exact area under the curve here, what this represents, is really just the value, the average value of the function times, the length of the interval, which is pretty crazy. It's saying this perfect area under the curve is average value times, or f of c times the length of the interval. So both of these are the same. They're the same statement. One is just, you do some algebra to get from one to the other. And remember, this double-headed arrow means both of these imply each other. So from here you can go here, or from down here you can go there with just some algebra. Okay, and again, this has a lot of very strong theoretical results, but it may not seem that interesting at the moment. Okay. And so let's just do one example from the previous thing, so you can kind of get maybe what I was saying. So the previous example we were looking at, f of x is 1 plus x squared on negative 1 to 2. And remember, let's just draw it again. So at negative 1, it was 2 units up, and then at the end at positive 2, it was 5 units up. And we said that this was the average value, was 2. So because this function is continuous on this interval, the mean value theorem for integrals tells us, remember MVT meant mean value theorem, for integrals we know that there is a number C such that could be more than one. This just tells you there's at least one. There is a number C such that f of C equals 2. So there has to be some number C that when you plug it into the function, it actually hits the output of 2. If there's not, then, you know, how can a function hit the average without actually one of the numbers being in there? Now, for like a finite set of points, this is not true, right? Like the average of, let's say, 90 and 290, two scores of 90s, or sorry, 90 and let's say 100. If you take 90 and 100, the average between those is at 85 or 95. But none of these numbers are 95, right? So in this case, it's not necessarily true that one of the numbers on the list had to be the average value. But this function is like, it takes on every single value between 1 and 5, the lowest number and the highest number. So it hits all of these numbers, and there's an infinite amount of them. So in this case, this does happen. It's pretty interesting. And so we know that there's some, at least one, where this is true, but we can calculate this number. Because what is f of c? Well, stick c into this. F of c is 1 plus c squared. And then if you set that equal to 2, you can actually solve for what c is. Subtract 1. So c squared is 1, and then take the square root. And then this means that c is plus or minus 1. These two numbers make this true. And we actually know that. If you stick negative 1 into this function, you get 2 out. And if you also stick positive 1 into this function, you also get 2 out. So these two inputs, when you stick them into the function, do give you the average value. And that's all that the MVT for integrals is basically telling you. It also has that cool property that it says, oh yeah, the area under the curve is just f average times the length of the interval. So another interesting thing about it is saying that this area here, the area under the curve, this area, this whole thing area, the blue area, is really just f of c, which is 2, is just 2 times 2 minus negative 1, which is 2 times 3, which is 6. Which we can, I'll confirm that for you guys real quick without having to do a lot of calculation. Yeah, it is 6. So the perfect area under the curve, you just multiply the average value times the length of the interval. So that's basically the two versions of the mean value theorem for integrals. And it has a lot of theoretical applications. But okay, I think that's enough for today, so I'll see you guys next time.